Hi everyone, my name is Madalina. I am a PhD student at the University of Oxford, and today I am going to talk to you about some work I've done with my collaborators in MIGHTEE-HI, and it's a paper that I put out, I think it's actually around last year this time. So yeah, I don't think the cosmic web needs an introduction anymore, because this is what we've been talking for about the past week, but I'm just quickly going to highlight that this is a massive network of matter and galaxies, and it has different environments such as voids, clusters, and filaments. And we, I think, all agree to some extent that it does have an effect on galaxies. And what we wanted to do is understand how does this effect influence the galaxies and to what extent. Again, we've all spoken about it this entire week, we've predicted it in the theory, we've looked at it in simulations, we've seen the strands of structures, we've seen the clusters, and then we realized in order to actually see it in observations, we need very large patches of skies. So we have actually seen it firstly in 1986 in this paper, which was a slice of the universe, if I remember well, where we could finally see the hints of this like large organization of the matter. And then ever since, we've been able to do better surveys with larger field of view, so like SDSS, SUMAS, and so on, to be able to actually see this network. Also, our old friend disperse, which a lot of people have mentioned it, use it in simulations to trace the filaments and all the cosmic web using the dark matter distributions. We can also use it on galaxies. So use the galaxies as the particles and hope that we're going to trace the cosmic web. And again, I think we've been extensively talked about how it works and how we can get all these critical points, how we can get all these filaments, these ridges, and these walls, and how we can control for all these parameters to ensure that we can get the best of our network. And here are some examples from the original paper of Sosby et al. In 2011. However, what I actually want to talk to you about more is neutral hydrogen. However, not in the same way we've talked about in the past few days. So we're not going to talk about absorption or Lyman alpha. We are going to talk about the emission line. So we're going to very low redshift. We observe emission in the neutral hydrogen with radio telescopes. And why do we choose to look at it? As you can see in this image, the H1 disk extends further out than the optical disk, which means we can calculate stuff as the position angle and the inclination of a galaxy with a better accuracy. And also, because it extends further out, it is more sensitive to tidal disruptions. It's also more sensitive to if we have cold gas accretion coming from the filaments. It's quite interesting to see how the H1 in these galaxies might be affected by it. Also, what we can also get from the H1 is we can get from velocity mass, we can also get dynamical mass of the galaxy, which might also be interesting to look at in relationship to the cosmic web. So specifically, the H1 alignments in literature with galaxies with the cosmic web in literature have not been studied very extensively. I am highlighting two studies today. One of them is a simulation by Madalina Tudorache et al. This was done in the SIMBA simulations, and what she found is that at an H1 mass of around 9.5, there is a flip between the spin being misaligned to being aligned. So basically, the orientation of galaxies flips for more massive galaxies. However, when Bluebird et al. In 2020 tried to look at this observationally using the Chile sample, they did not find this split. The only thing they found is that the H1 selected sample tended to be, on average, more aligned with the filaments than misaligned. However, what I have to really make a point here is they only use 10 galaxies. So in terms of statistics, it's probably not the most robust. So what did we do? For the filaments, we used the data from the Cosmos MSS fields. This is a picture of the video survey. So we use these fields because they are some of the most extensively researched fields. and we have optical and near-infrared data, like across a lot of have very good data for that, so we can use that to trace our filaments. And we chose these two fields because, as I was showing in the picture at the beginning, we can look for in different environments. So having shallower, larger patch of sky, or a smaller patch of sky that might encompass a different environment, and that's why we chose this. So with that, this is what we obtained. So we used the spectroscopic redshifts. We did it on a redshift range from 0.02 to 0.09. We had to restrict to this redshift range because of A, on the lower end, we didn't have enough spectroscopic redshift to be able to trust our filaments, and B, the higher end was mostly limited by the H1 detections, because our highest H1 galaxy is around 0.084, so we had to stop. So in this figure, we just have them 2D projections of array depth and cumulative distance. The blue lines are the filaments. The black points are the optical and near-infrared galaxies we use to trace the filaments. And the red stars are the H1 galaxies, which I'm going to talk about in a second. So I mentioned that we met, also if anyone's interested about all the parameters, everything that I use for disperse, you can always ask. But we use mirror boundary conditions to be consistent with the Bluebird work, which they also use disperse and mirror boundary conditions on their network. So we use them, similar things, to be able to draw comparisons to what they got. So I mentioned radio telescopes, and I mentioned getting H1 from radio telescopes. This is MIGHTEE-HI. This is a radio interferometer in the Karoo Desert in South Africa. It's been operational for more than 3 years. This is an SK precursor. We've been getting a lot of data out of it, and it's all very good data. Like, there's been a lot of radio stuff coming out recently. It's most likely to be from MIGHTEE-HI. So within it, I'm going to highlight the MIGHTEE survey, which is a radio survey in L-band that spans this frequency range. It goes in 4 fields. However, we're only interested in 2 for this work, which is the cosmology analysis, as I've said. In terms of how good it is, by comparison, so from 16 hours of integration, we can get 1.8 microjansky. So VLA Cosmos would need 20 times the time to reach a similar sensitivity, or maybe if you're an optical astronomer, it's the equivalent of an integral field spectrograph with 1 square degree field of view and 33,000 spectral channels. I didn't know how to draw comparison with simulations, but so this is what we get in radio continuum. These are all radio galaxies, and you can see how well we can get data. These are not all H1 galaxies. However, from now we can also get our H1 galaxies. So yes, this is MIGHTEE-H1, which, as I said, is the H1 emission project within the MIGHTEE survey. From the early release data, we've managed to get 270 H1 galaxies, which you can see some examples. This is one at actually 0, so you can see what a good map we can get. However, when we go higher, we have to work a bit harder to get our information out of them, because it's we need to focus a bit more to find. And these are all the radio maps. However, for our study, we could not use all 270 H1 galaxies, because if we look at the maps, we have some of them which are really good, from which we can extract kinematics, and extracting kinematics is what gets us the position angles and the inclinations, which I've mentioned that we need to use in our work. Then in some of them, you might have to use precaution to calculate. So for example, if you have a face-on galaxy, so if the inclination is between 0 and 10, you can't really tell if it's slightly like this or if it's just like this. So we've chose to ignore all those galaxies to where we weren't really secure in how good our measurements were. And then you have galaxies like this where you can't get anything out of them. Or at least with the current data, when the full MIGHTEE survey will come out, we might be able to resolve some of these as well. So now that we've gone through all the data we have. What did we actually do? So, using the H1 data, we calculated the spin vector. Then what we did is we used our filament network from disperse. For each galaxy, found its closest filament, and then we took the dot product between the two. So, and then from that, we got out the cos angle. What should be mentioned is that because our filament doesn't have a meaningful direction, we took the absolute value of the cosine of the angle. So basically, we have our cosine will range from 0 to 1. And to keep with convention, what we said is that we split it in 0.5. If it's from 0.5 to 1, then it will be a line. And if it's 0.5 to 0, then it is considered to be misaligned. And this is what we did. Then we decided to look at how does this correlate to different parameters related both to the environment, so both to the filaments, and related to the properties of the galaxies. So first of all, we looked at distance to filament and how does that relate to the spin angle. So what we found is, I'll draw your attention to this area because this is where we have the most significant result. So we found that the closer you are to your filament, the more likely you are to be aligned. So filaments that are closer will have their spin parallel to the filament. And then if you go further, our results are very noisy. So in this graph, anything that's above 20 megaparsecs, you can see the cosine is 0.5, which basically means it's a random effect. We tested our results using the KS test. So we shuffled all of our PA's position angles and inclinations, and then we shuffled them between the galaxies. We recross-matched everything, and then we recalculated all the angles, and we did that 2,000 times, and then compared all these distributions, and we got that this is a statistically significant result. In order to quantify for the errors from the fact that we're not quite sure about if our filament networks are correct and all of that, what we did is we took all our optical galaxies again, we randomly took out 5% of them, redid all the filament networks, redid all the cross-matching, all the angles, and calculated again for each of the galaxies what's the cos angle. So all these error bars come from doing that method around 100 times. And then you can see it's cut between 0 and 1 because it doesn't make sense for it to go negative down. Then we also did the H1 mass to see if we can see that spin transition. So we split our sample at the median value, which was around 9.78. What we found is, well, not a lot. We found that there was a slight tendency for alignment for the ones with a lower H1 mass, and there was just random for the higher H1 mass. However, when we tried to compare the two distributions, the one with the lower and one with the higher, using the Mann-Weinert test, we found, which looks at the medians of the distributions, we found that they're not very different. So there's no statistical significance. And we also looked at the correlations, and we also found that there was no correlation in between the cos angle and the H1 mass. Further, we looked at the baryon mass fraction, which is just the fraction between the mass of the baryons, so the gas and the stars, and the dynamical mass that we get out of the H1 data. Same thing, we split at the median value of our sample, and what we found is that galaxies with a lower baryon mass fraction tend to be misaligned, while galaxies with a higher mass fraction tend to be more aligned. So if you have more dark matter, this is what it's saying, is you're more likely to be aligned with your filament. However, once again, when we did any statistical tests on this, it turned out none of the correlations, none of the tests said that this is actually anything significant, which we might boil it down to the fact that we don't have enough numbers. This is still 77 galaxies. However, what was the interesting thing is that we found the relationship between the H1 stellar mass fraction and the cosangle. So again, by doing the same thing, we split the median of the sample, and what we found is that the galaxies with a lower H1 stellar mass fraction are more likely to be aligned, and the galaxies with a higher stellar H1 stellar mass fraction are more likely to be misaligned. And then the same thing was reflected in the correlation there. So we saw the same trend going down. So this is not something we expected. This is an empirical relation. The way we attempt to explain this is probably via mergers, specifically gas-rich mergers, who might increase the amount of H1 gas, so increase the fraction of H1 to stellar mass ratio, and also just disturb the disks and disturb the alignment between the two. So this was basically the things we've done using, so to quickly summarize everything before actually going to my conclusions and what I think will be some future interesting things to do, is we use this first to compute filaments based on the Cosmos XMLSS spectroscopic catalogs. We cross-matched these filaments with the H1 galaxies from the MIGHTEE-HI survey, and we found that two parameters correlate. So we found a distance to filament, that the closer you are to the filament, you correspond to a more aligned spin, and the lower H1 to stellar mass ratio you have corresponds to aligned spin. So these are the takeaway graphs, I think, of this talk. And probably what we found is that stellar mass as well as proximity to filaments will affect your spin as a galaxy and your alignment to your alignment. And specifically, most galaxies have probably not undergone a merger, so they're more likely to be aligned. But the ones that have undergone a merger, there's a chance, if they have undergone a gas-rich merger, for them to have disrupted their spin alignment. And in terms of future work, what we can also explore is looking at the morphology of the galaxies, because the thing by using an H1 selected sample is that we're quite biased, so we don't get any massive early type galaxies. All of our galaxies in our sample are disk galaxies, and there have been studies that show that most of them are more likely to be aligned than misaligned, for example, whilst the studies have shown the more elliptical galaxies are more likely to be anti-aligned. So this might help us understand other correlations, for example, the baryon mass fraction. We can also explore the possibility of looking for the hints of mergers by using SD fitting of our galaxies. This is a very quick example of what we can do with the code bagpipes. So just looking at star formation histories and see if we can see in the galaxies that we found to be misaligned if there are any hints of mergers. Exciting! The full MIGHTEE survey will provide thousands of H1 galaxies. So we started with 77. We can extend this much further, and we can go on a much larger scale. So for this, this was 6 degrees square for the work I've just shown. We're going to go at 20 square degrees. So this is going to improve massively in terms of numbers and statistics. And all I've done was using spectroscopic redshifts. We should be able to use photometric redshifts to also improve our filaments. This is an example of trying to use photometric redshifts and their associated uncertainties on how to compute filaments. And I probably don't really have time to talk about this, so we can always ask me about this later. And I will leave you, well, back with the conclusions. So if anyone has any questions, please let me know.
How many microphones we have? I'll start with this one.
Hi, very interesting talk. Thank you. Basically, I'm just curious, why did you choose the cosine? I mean, I see a lot of people, that's kind of, I guess, became traditional in this field, but in terms of, for instance, contrasting against a null hypothesis. Like if I think about the simplest null hypothesis I could think of is you have random distribution and there's no correlation, in which case you would have a uniform distribution in the angles, and that would be very easy to test whether it's, consistent with that. Right now, what I see here is like you have all these points kind of randomly distributed, and then when you average them, of course, you'll get 0.5, whatever that means. So it's very hard for me to interpret these results, and each point has an error bar. So in the end, that 0.5 will have actually a pretty good error bar, and then any fluctuation will look like semi-significant. I'm just wondering, there's a billion ways to do this. Why exactly cosine, and whether you plan to do something different that would be statistically a little bit easier to interpret.
So you mean as in, instead of using the cos angle, just no use angle? What? I'm not entirely sure what the question. As in, what else?
Well, the question is, how did you choose cosine
chose
among the billion possible ways of characterizing these things, and what was your null hypothesis that you're trying to test?
So we chose the cos angle because we wanted to be able to do comparisons with all the studies that have been done before. So in this field, most people have used the cos angle. So basically, well, I think actually the Bluebird and all, they actually just use the angle, but going from cos angle to angle is just about taking out a cosine, so that doesn't really make any difference. But I think even if you have a flat distribution in cosine and you take it back into angle, does that make it a Gaussian, like random, or is it the other way? I think there was something we noticed when you switched from cosine to angle. If it was a normal distribution, and the other one would be a flat distribution. So I think that's why we decided that we can go either way.
Thanks. I'm very curious about the last figure where you show the correlation of this alignment versus H1 mass. I wonder, among these small set of sample, will you be able to look at their optical counterparts to see their properties, and if there's any hint for the optical morphology, for example?
Yes, so people have actually started cross-matching the H1 catalog to the optical and near-infrared data. So we do currently have optical morphologies for some of these things, and we are already looking at them. I don't have any current results of them, because I think in the 270 there's still mostly the sample is this Galaxies. I think there's 4 early type and like 11 irregulars, if I remember right. But yes, we have started cross-matching our optical data with the H1 to be able to see optical properties in the Galaxies as well.
Right.
If you have a chance to comment on observation.
No, I mean, I first want to say it's great to see long wavelength data being used, because I'm a big fan of long wavelength data. I mean, maybe it's connected to Istvan's question, but you have inclination here, which is different from most optical samples where it's all 2D projection. So there's a different thing going on when you ask whether the spin axis is aligned with the filament than there is if you're just doing a 2D projection. So I just wondered if you'd explored that. So for example, just saying, what if I just had the 2D projection? So how much better do I do the alignments when I have the inclination as well, right? Because it's better, right?
Yeah, I mean,
surely
in 3D, it's probably be better. Yes, we haven't looked at how does it make a difference. It'll probably be interesting to see. But also have, because technically you can get inclinations from stellar data, right? But then usually you're not sure if you can get the inclinations as well. And then there's also the chance of having your gas disk and your stellar disk being slightly misaligned, right? So you get slightly different inclinations.
And you typically don't even know if it's a disk in the optical. So you basically just have a 2D. I mean, really good optical data on individual galaxies is different. But I mean, I think it's worth looking into, because then you can say radio is better. Right?
Yeah.
Which would be good.
Well, my comment was going to push back a little bit on that which is that your redshift range is exactly overlapping with SDSS, which is not just in the sense, so you don't just have the imaging of SDSS, you have the full spectroscopic catalog, and even the full cosmic web catalog has been published for SDSS, and spanning much larger fields of view than so it does include Cosmos, but it goes beyond your boundary. So that might be a useful check. For example, like the boundary effects that your cosmic web finder might be experiencing.
Karantan and sorry. You're supposed to answer.
I thought, is there a comment?
Okay. And the next speaker, please start.
So my question is that in the bottom right panel, essentially you're probing different H1 masses, which if you convert that to a spatial extent, depending on the depth of your observation, you're probing larger distances compared to the center of the galaxy. So could you explain, well, is it possible that the signal you're seeing is just because you're looking at stuff that are further and further away from the galaxy? And because you may have an H1 disk that you can't see because it's below your resolution limits, that is still rotating faster, but you don't see it. So in other words, if you were to cut at a fixed radius, would you still see the signal?
Good question. We haven't looked at that, but that might be interesting to look at because we have the H1 radius, we have the radius for each of our galaxies, so we could technically apply a cut and see if that makes any difference. So yeah, that's an interesting point. Thank you.
All right, so let's thank the speaker once again.
Thank you.